There we go. Okay, so our final talk of the day is J Nicaise from Imperial College and KU Leuven, and he's going to tell us about toroidal degenerations and stable rationality.
Well, many thanks for the invitation. And well, I feel I should start with a round of apologies first to Evelyn and Daniel for missing their, I'm sure, excellent talks. I was teaching algebra this afternoon until half an hour ago. But I'll make sure to watch the recordings. But then also to everybody who has seen a variant of this talk in the last couple of months, because with everything that's been going on, it has been hard to squeeze in some new research recently. So I'm afraid, the results I'm going to present are not as fresh as could be hoped. But yeah, at least I hope you'll get something out of it. So what I'm going to present is based on a work in progress with John Christian Otten. And the general aim is to use prior results with Yevgeny Schindler on specialization of stable birational types, together with new input from toroidal or tropical geometry to come up with new examples of non-stably rational complete intersections. And the leading example will be the quartic fivefold, but I will explain what other results can be obtained. And in fact, the main message is that the method is much more general. So I'm sure there are other applications out there which can still be explored. So I'd like to start with an introduction just to explain what the main problem is and what we know and what we would love to know. So first of all, a complex algebraic variety X is called rational if it's birational to a projective space. And then a slightly more subtle notion is stable rationality, which means that your variety becomes rational if you multiply it with a projective space of sufficiently high dimension. And obviously, rationality implies stable rationality, and it's been an open question for a while whether the converse implication was true or not, until finally in '85, Beauville, Collier-Telaine, Sansuc, and Swinerton-Dyer produce an example in dimension 3 of a stably rational but non-rational variety. So in dimension 1 and 2 by Lurot and the Enriquez classification, both notions are equivalent. But from dimension 3 on, they start to diverge, and stably rational is strictly more general than rational. And so the type of question we are trying to understand is the stable rationality of very general hypersurfaces in projective space. And so the dimension of my hypersurface will be denoted by n, and the degree will be denoted by d. And so very general means well, my hypersurfaces are parametrized by some projective space. Well, my linear system of degree d hypersurfaces in projective n+1 space. And so I'm interested in a stable rationality, or whether this property holds for a very general member of this linear system, meaning every variety in a countable intersection of dense open subsets of my linear system. And you will see in a bit why general is not enough, while very general is the proper notion to use in this context. So I've made a table to indicate what is currently known. And so this is somehow the low-hanging fruit, or what is classically understood. So of course, linear hypersurfaces are all rational, and also quadrics are all rational. And then there's the funny accident that the cubic surface is rational. And then in the red zone, when the degree is at least a dimension +2, then we're out of the Fano range. So all of these guys are, well, not even unirational, so certainly not stably rational. So that's what you get from classical techniques. And then so the first new cases, well, first burst of activity occurred around the 1970s on generalization of the Lurot problem to higher dimensions. And so the relevant results here are, first of all, a result by Clements and Griffiths, who proved that cubic threefold is not rational, using the intermediate Jacobian as an invariant. So I've checkered the box because we still don't know whether a very general cubic threefold is stably rational or not. It's kind of surprising that this is still open. And then for quartic threefolds, so the rationality or non-rationality better was settled by Iskovsky and Manin in '71. But only much more recently in 2016, Collier-Telaine and Pirutka, they proved that a very general quartic threefold is not stably rational. If we go up in dimension, so for fourfolds, of course, the $1 million question is the cubic fourfold. If you can say something here, you'll be rich and famous. And then for the degree 4 and 5 cases, so quartic and quintic fourfolds, it was proved by Totaro in 2016 that very general quartic and quintic fourfolds are not stably rational, so they also lie in the red zone. In fact, these cases are special cases of a much more general result by Totaro, improving on an earlier result by Collard. And the crucial input for Totaro was a new method on specialization and decomposition of the diagonal due to Clairvoisin. But then Totaro's results were further absorbed by the work of Stefan Schreider. And so this is the best known general bound that we currently know. So Schreider proved that, well, there's an asymptotic bound on the degree at least log 2 of n plus 2, such that above this bound, all of our very general hypersurfaces are non-stably rational. And so that's the strongest result that we currently have. And everything in white is still open. And in fact, it's expected that a substantial part of our diagram should be red. I'm not sure if there's really a solid conjecture, but at least there's a folklore expectation that outside of the surface case, very general cubics should be irrational, and all smooth quartic hypersurface should be non-stably rational. So from degree 4 on, everything should be red. But what we know is actually much less, because as you've seen, even Schreider's result has a bound on the degree that increases logarithmically with the dimension. So we don't know any value of the degree such that a very general hypersurface of this fixed degree is non-stably rational in all dimensions. For degree 1 billion, it's very probable that all very general hypersurfaces of degree 1 billion are non-stably rational, but we don't know how to prove this. So before explaining the method, let me showcase a couple of results that we've been able to obtain. So I will first discuss a few results for hypersurfaces and then comment on complete intersections more generally. So the first new result, whose proof I want to explain completely today, is that a very general quartic fivefold is not stably rational. So that's somehow the first case outside of the boxes we already knew. And then, in fact, our result is a bit more general. We get a partial induction, but I'm not sure how useful it really is in practice beyond the case of the quartic fivefold. So what we really prove is that if you know non-stable rationality of a special quartic in dimension n-1, and we have different versions of the theorem with different interpretations of the word special. But if you manage to prove non-stable rationality of certain special quartics in dimension n-1, then you can deduce non-stable rationality of very general quartics in dimension n. So it's some kind of induction on the dimension, but it's not a true induction because we don't know how to go from very general to special in dimension n. We get an actual induction on degree and dimension in the following sense. So if you manage to prove non-stable rationality of a very general hypersurface of degree d and dimension n, then you also get degree d plus 1 in dimension n and degree d plus 1 in dimension n plus 1. And then finally, if you look at hypersurfaces in products of projective spaces, the method also allows you to classify all the hypersurface in products of projective spaces up to dimension 5. So there you get complete answers. So for the hypersurfaces in projective space, so points 1, 2, and 3, I try to illustrate them also on the diagram. So the quartic fivefold case is the dark red box here. So the first box outside of the diagram in degree 4. And then the hollow arrows, well, they represent my fake induction. So we can try to increase the dimension, except that the conclusion of our induction process is a bit too weak to make the following step in the induction process. We get a genuine induction with a full red arrows. So we can move up in degree and remain in the same dimension, or we can move up in degree and dimension simultaneously. So yeah, this is just a sample of results. So the question is also of interest if we look not at hypersurfaces, but at complete intersections. And so then the further results we obtain with similar techniques are, first of all, very general 2-3 complete intersections in P6 are non-stably rational. And this is a significant case because except for the notorious cubic fourfold, this was the only open fourfold case. And so this we were able to settle by means of our method. Going up to dimension 5, we proved that very general complete intersections of by degree 3-3 in P7 are not stably rational. And then we also get some general bounds, so a Schreider type bound for complete intersections instead of merely hypersurfaces. But we don't reprove Schreider's theorem. In fact, we use Schreider's theorem as input. But just a special case to give you an idea. So what we show, among other things, is that very general complete intersections of R quadrics in a projective space of dimension n plus r are non-stably rational when n is at least 4 and the number of quadrics r is at least n minus 1. And so this extends previous results by Hassett, Perutka, and Schinkel, and Chatzistamathieu and Levin. Yeah, once again, what I want you to take away from this talk is maybe not so much the particular cases where we have applied the method, but more the general method in itself. So in fact, all of these concrete applications are special cases of more general specialization results for stable birational types. And so the main ideas are, first of all, well, the work with Yevgeny Schindler that I referred to earlier. So with Schindler, we constructed some kind of nearby cycles functor, a specialization map for stable birational types. And so what comes out of this is that for every strictly toroidal degeneration, and I will define in a moment what this means, but you get an obstruction to stable rationality of the geometric generic fiber of your degeneration. So if you have a strictly toroidal degeneration, proper degeneration over a curve, then you can compute a certain invariant which forms an obstruction to stable rationality of a very general fiber of your degeneration. And this is the essential instrument that we use to settle these new cases. Of course, if you want to apply such a method, you need a source of strictly toroidal degenerations. And fortunately, there's an extremely efficient mechanism to find such degenerations, namely tropical geometry. So this goes back, well, many decades to pioneering work by Kushnirenko and Viro on Newton non-degeneracy and patchworking polynomials. And then more recently, the tropical geometry over discretely valued fields was worked out by Tievelev and Luxton and Xu. So these are the tools that we are going to use. By the way, feel free to interrupt me at any point if there are any questions. If I'm speaking too fast or going too slow. So first of all, I'm going to set up this specialization mechanism for stable birational types. Well, just to start with some notation. So over general field F, we say that two integral F schemes of finite type X and Y are stably birational. If they become birational, if we multiply X with a projective space of sufficiently high dimension, and if we multiply Y with a projective space of sufficiently high dimension, but the two dimensions need not be the same. And so this is related to our earlier notion of stable rationality in the sense that stably rational is the same as being stably birational to a point. So this is an equivalence relation such that stably rational varieties form one of the equivalence classes. And so I look at a set of all the stable birational equivalence classes of integral F schemes of finite type. I call this set SB of F. And then we can attach a stable birational class to schemes of finite type, which are not necessarily integral. Just by decomposing a scheme into its irreducible components and taking the sum of the stable birational types of the irreducible components. And this sum makes sense in the free abelian group on the set of stable birational equivalence classes. And it seems kind of naive to consider just formal integral combinations of stable birational types. But in fact, computing in this group is going to be the full power of the method. And this is not only a group, it's also a ring. There's an obvious way to define a multiplication by saying that the product of the stable birational types of X and Y is the stable birational type of the product. So it's easy to see that this is well defined independent of the representative. And so what we want to understand now is if we have a one parameter degeneration of varieties with sufficiently mild singularities, we want to understand what happens to the stable birational type of a fiber when we approximate the degenerate fiber. So this is what the specialization map is going to do for us. And so to set up this specialization map, well, we want to work over some kind of universal curved germ. So in first instance, we could try to work just over the ring of formal power series in one parameter T, which is the algebraic avatar of a small open disk in complex geometry. But to make the construction work, we also need the liberty of passing to a finite ramified cover of the disk at any point. So in order to do this in a universal way, we just take the universal ramified cover. So algebraically, this means that I take the union of the power series rings over all roots of T. And in fact, this is a ring with a very nice algebraic structure. So it's a valuation ring whose quotient field is the field of Puiseux series, the standard algebraic closure of the field of complex Laurent series. So I'm going to work over this valuation ring to have some uniform setting where I can discuss one parameter degenerations of algebraic varieties. And so the kind of degenerations I want to allow are the strictly toroidal degenerations. And so the definition will be a bit technical if you have never seen this before, but on the next slide, I'm going to show you the two most important examples for the purpose of this talk. So over this valuation ring, a scheme of finite type is called strictly toroidal. If locally for the Zariski topology, it's smooth over a scheme of standard form. And our standard form is the spectrum of our, well, the algebra, the monoid algebra over our valuation ring attached to a toric monoid M. So toric monoid means just the semigroup of lattice points inside strictly convex rational polyhedral cone. So the kind of semigroups you encounter in toric geometry. And then I look at a subscheme cut out by an equation of the form chi to the power m minus t to the power q. Where q is any positive rational number, and where m is an element of my monoid. So chi to the power m is the corresponding character, and I impose that when I look at the zero locus of chi to the power m inside my affine toric variety spec CM, that the zero locus is reduced. So these are the conditions that I impose. Again, if you've never seen this before, it's kind of hard to visualize what's going on. So let's look at two main classes of examples. So a subclass of strictly toroidal models are the strictly semi-stable models. And so these have a stronger property. They are Zariski locally smooth over, well, a standard model of a more restrictive kind. So I look at the affine n+1 space over my evaluation ring. And then inside, I look at the equation product of the variables equal to t to the power q, where q is again any positive rational number. So these strictly semi-stable models are, well, they appear in many applications in algebraic geometry. And one crucial property is that there are plenty of them, in the sense that every smooth and proper variety over our Puiseux series fields has a strictly semi-stable proper model over the valuation ring. And so this is a consequence of resolution of singularities over any finite extension of the Laurent series field or the power series ring inside this valuation ring. So at least this guarantees us already that there are a lot of strictly toroidal models. But how they arise in practice in the context we're interested in is in the following way. So I'm going to show you an example of a strictly toroidal degeneration, which is not strictly semi-stable. And this example indicates why it's important to have this more general class of models to work with. So I can look at a general homogeneous polynomial of degree d over the complex numbers in variables z0 up to zn. And This defines a degree D hypersurface in projective n space. And I'm going to set up a degeneration that breaks up my hypersurface into hypersurfaces of smaller degrees. So I pick general homogeneous polynomials G1 up to GR, such that the sum of their degrees is equal to D. And then I can look inside projective n space over my valuation ring at the subscheme defined by T times F minus product of the GI equal to 0. So this is strictly toroidal. It's locally modeled after a toric variety. It's not going to be strictly semi-stable, but this is the kind of degeneration that will allow us eventually to set up induction arguments on the degree. Because if I look at the generic fiber of this model, so if I look at what happens over the Puiseux series field where I've inverted T, then this is a degree D hypersurface inside projective n space. On the other hand, if I look at what happens in the special fiber, the degenerate fiber, well, I put T equal to 0 in my equation, and there I get a union of R hypersurfaces of smaller degrees. And so this will fuel our induction mechanism. So if curly X is any strictly toroidal scheme over my valuation ring, then its special fiber is not too singular. So locally, it looks like a union of toric varieties intersecting along toric boundary divisors. And there's a natural way to define a stratification on this special fiber. So a stratum of the special fiber is just connected components of an intersection of irreducible components of the special fiber. And by codimension of a stratum, I will mean the codimension inside the special fiber. And so in particular, if we have not only strictly toroidal model, but a strictly semi-stable model, the special fiber will be even nicer. Then it's just a union of smooth varieties that intersect transversely. And that's a good example to keep in mind. So the specialization map that we defined together with Yevgeny is the following. So we show that there's a unique ring morphism from the ring of stable birational types over the Puiseux series fields to the ring of stable birational types over the complex numbers. And so this specialization map detects how stable birational types degenerate for families over my valuation ring. And so it's uniquely characterized by the following property. If I have any strictly toroidal proper model, curly X, then I can give as inputs the stable birational type of the generic fiber. And so the output will be an expression, will be a virtual stable birational type over the complex numbers, which arises as an alternating sum of the stable birational types of the strata in the special fiber, where the sign is given by the codimension of the stratum. So of course, it's not at all obvious that this thing exists, that it's well defined, that it's independent of the model, that it's compatible with stable birational equivalents and so on. And so all of this relies on weak factorization in an essential way, which allows us to compare different strictly toroidal models of the same generic fiber. And then some logarithmic geometry to keep the calculations manageable. But in this talk, I don't want to say anything else about the proof. I want to show you the applications. So how are we going to use the existence of this morphism? Yeah, sorry, I should probably explain. So we picked the notation vol for the specialization morphism. Vol stands for volume, and the reason is that an upgrade of this morphism also appears in the theory of motivic integration, where it's actually some kind of volume that is associated to algebraic sets or semi-algebraic sets over the Puiseux series field. So there's a whole history and work by many other authors behind this construction, but I don't want to go too far in that direction today. So one thing we can observe is that, well, what happens when we apply this morphism vol to the class of stably rational varieties over the Puiseux series field. So this means we take as input the stable birational equivalence class of a point. And then, well, the point has an obvious strictly toroidal model, namely just the spectrum of the valuation ring. And then the special fiber of this thing will be just a point over C. So by definition, vol sends stable birational, again, sends stably rational varieties over the Puiseux series field to stably rational varieties over the complex numbers. And so this means that if you give some input to your morphism vol and the output is anything else than the class of a point, then this means that your input was not stably rational to begin with. So in this way, vol gives you an obstruction to stable rationality of the generic fiber of your degeneration. So maybe before showing you the applications, let me try and motivate why this type of formula is not unreasonable. And first of all, one way to interpret it is as some kind of inclusion-exclusion game. So what the volume gives us is the sum of the stable birational types of the irreducible components in a special fiber. But then we're overcounting the intersections of these components. So we subtract the intersections, but then we're undercounting the triple intersections. So we add the triple intersections again. And so this alternating sum is not an unreasonable candidate for the virtual stable birational type of the special fiber. So in that sense, yeah, what vol does is it gives us output the virtual stable birational type of the special fiber of any strictly toroidal model. There are deeper reasons behind this formula, which are related to Hodge theory. So this is also the kind of expression you get when you compute the limit mixed Hodge structure by the weight spectral sequence. Yeah, again, if you haven't seen this before, that doesn't mean much at this point. Already a very significant special case is what happens when your model is actually smooth. So when also the special fiber of your model is smooth. So in this case, there are no double intersections at all. And so the output of the morphism vol will just be the stable birational class of the special fiber itself. And so in particular, this class is independent of the representative that we choose on the left-hand side. So this means that specialization in smooth and proper families respects stable birational equivalence. In particular, stable rationality of geometric fibers specializes in smooth and proper families in characteristic zero. So this was an important application that appeared in the work with Yevgeny. This was an open problem in algebraic geometry at that point. And to make this a little bit more precise, so what we proved is that if you take any Noetherian scheme in characteristic zero as a base, you take a smooth and proper family X over your base scheme S, then, well, you can look at the locus of points in the base such that the fiber is stably rational. With the caution that instead of taking the fiber, what we are taking is the geometric fiber, which means that we are extending the field of definition to an algebraic closure to get a geometric notion of stable rationality. And so what our result implies is that this locus of stably rational geometric fibers is a countable union of closed subsets of S. So it's easy to show that it's a countable union of locally closed subsets. That follows from a Hilbert scheme argument, and that was known long before. But since it's also closed under specialization, you get a countable union of closed subsets. And what this means is that if your base is irreducible, then either all geometric fibers of F are stably rational, or a very general geometric fiber is not stably rational. And so either the locus of stable rationality is just everything, or it's a countable union of strict closed subvarieties, but that means that a very general geometric fiber is not stably rational. And so in order to show that a very general fiber is not stably rational, it's now enough to find one fiber which is not stably rational, which is a much easier task, of course. So one can ask if the same result still applies if we replace stable rationality by rationality. So that the answer is yes. This was proved by Kontsevich and Chinkel shortly after, using a similar method, but refining the morphism vol to the level of birational types. But in fact, in this talk, we'll be mainly interested in disproving stable rationality by means of our obstruction. And then, of course, you disprove rationality at the same time. So as an obstruction on the level of stable rationality, you actually have a stronger instrument. So the rest of the talk, I want to look at situations where obstruction does not vanish, and so we get statements about the non-stable rationality of generic fibers. And so as a first application, I want to give you a short proof of a theorem due to Claire-Voisin from 2015. So this is one of the first applications that Voisin gave of our new specialization method. And so she showed that a very general quartic double threefold over the complex numbers is not stably rational. And so quartic double threefold means a double cover of projective tree space, which is ramified along a quartic. And so what I just explained by our specialization results, instead of proving this for a very general guy, we just need to find one. And in fact, we can choose the base field of the one counterexample in any way we like, as long as it has characteristic 0. So it's enough to find one non-stably rational quartic double threefold over some algebraically closed field of characteristic 0. And well, the field we're going to use is the field of Puiseux series, because there we can apply our degeneration technique. And so we always need some kind of non-trivial input to make this method run. And so here we use classical results due to Artin and Mumford, which also goes back to the 70s. So Artin and Mumford, they gave an example of a non-stably rational quartic double threefold, which is not smooth, but which has isolated ordinary double point singularities. And so we pick such an example, and I will denote it by Y. And then we are going to smoothen Y in order to get a smooth example. And so we can do this by looking at the ramification divisor of our double cover of projective tree space. And so by smoothing this divisor in a general pencil, we get a double cover, or rather a family of double covers of P3 over the line, where the special fiber is just the Artin-Mumford example, and the generic fiber is smooth. So this is not yet the type of degeneration that we can work with, because it's not going to be strictly toroidal. And so in order to remove the singularities or improve the singularities, we first blow up at all the singular points of the Artin-Mumford special fiber. And then, well, we perform a base change to our valuation ring and we normalize. And so the result of this blow up procedure is that we now have a strictly toroidal degeneration. In fact, it's even going to be strictly semi-stable. The generic fiber of this thing is a smooth quartic double threefold over the Puiseux series field, and we're going to show that this guy is not stably rational. And so we compute the obstruction that is provided by the morphism vol in this case, and so this is easy in this example because the special fiber has only one stratum that is not stably rational, namely the strict transform of the Artin-Mumford threefold. And so on the next slide, I've drawn a picture. So this is the special fiber of my degeneration of my semi-stable model. So in green, you have the strict transform of the Artin-Mumford example. And so I know that this is not stably rational by the work of Artin and Mumford. And then in black, you see the exceptional components that I have created by blowing up my singularities. So all of these will be rational. This you can compute explicitly since we've just blown up ordinary double points. And then, well, so these are all my strata of maximal dimension. And then I also have a bunch of strata of codimension 1, which are the intersections of the exceptional components with my strict transform. But again, a calculation on our blow up shows that all of these are rational as well. So the green guy is not stably rational. The black and yellow guys are rational. So now I compute my obstruction. So I compute my alternating sum. And what's going to happen is that, well, since the black guy is always going to be stably birational to the yellow one, since they are both rational, the black contribution is going to cancel out with the yellow contribution since they have opposite signs. And the only term that is going to survive in my formula is the term corresponding to the strict transform of Y. Which is the stable birational class of the Artin-Mumford example. which is not a class of a point, since the Artin-Mumford example is not stably rational. And so since our output is not the class of a point, our input was not stably rational, and this is exactly what we wanted to prove. So I hope that this application demonstrates how to use the method. But of course, if you want to find strictly toroidal models, it can actually be quite painful to compute them by hand. If you start from a random degeneration, then resolving the singularities by hand can be extremely complicated and almost impossible to control in practice. So we'd like to have an abstract method that generates these degenerations for us. And so this method is tropical geometry. And so I'm going to give you a crash introduction to tropical geometry, or at least the bits and pieces that I'm going to need. So here we start from a Laurent polynomial over the complex numbers, where the exponents are the lattice points of, or the elements of the lattice z to the power n+1, and the coefficients are denoted by Cm. And to such a Laurent polynomial, we can attach some combinatorial gadgets. First of all, the support, which is just the set of exponents with non-zero coefficients. And then the Newton polytope, which is the convex hull of the support. I'll show you a basic example in a second. But the message of tropical geometry is that if your polynomial is sufficiently general, then the shape of the Newton polytope will give you a lot of geometric information about the polynomial f. And in particular, it will give you geometric information about the zero locus of f, which we are going to denote by z of f. And so this is the zero locus inside of the n+1 dimensional algebraic torus. So a simple example, which is going to return in our final application, is well, an example of an elliptic curve. So a quartic double curve defined by y square is equal to f for x, where f for x is a general quartic polynomial in x. So my support consists of all the blue dots in the picture. I have 5 blue dots corresponding to the 5 terms of my quartic polynomial. So these don't involve y. So here the vertical coordinate is 0 and the horizontal coordinate ranges from 0 to 4. And then I have one more term, y square, which gives me the point 0,2 in my support. And then the Newton polytope is the convex hull, so that's going to be the blue triangle. And well, this blue triangle contains other lattice points, which would be the linear terms in y, but somehow these won't matter in the story. And so what I'm going to do now is I'm going to set up degenerations by means of some reverse engineering, which means that I'm going to start from tropical data or combinatorial data, and I'm going to use this to generate varieties and degenerations. So if I pick any lattice polytope delta in n+1 space, then I can consider polyhedral subdivisions of delta into lattice polytopes. And in fact, to generate degenerations of algebraic varieties, we need an additional condition on the polyhedral subdivision, which is the notion of regularity. So we say that such a polyhedral subdivision is regular if it's induced by a convex piecewise affine function, in the sense that we can find a convex piecewise affine function from our polytope delta to R, such that the domains of linearity of this function are the maximal faces of my polyhedral subdivision. And so convex piecewise affine functions, they generate polyhedral subdivisions in this way, and any subdivision that can arise in this fashion is called regular. So an easy example is this one. So you get the lattice polytope in orange. And then in blue, you see the graph of a convex piecewise affine function defined from my orange polytope to R. And you see by looking at the domains of linearity, you get a polyhedral subdivision, which is also drawn on in the horizontal plane. So this would be an example of a regular subdivision. It's not so easy to come up with examples of subdivisions which are not regular, but there are plenty of non-regular ones. So it's an important condition to take into account, but still, well, sufficiently general to be useful in practice. So now assume that we have such a subdivision, and now I'm going to select coefficients for my polynomials. So for every lattice point inside the polytope delta, I'm going to choose a corresponding complex number, C. And I'm going to impose a condition that when I pick a vertex of my subdivision, the corresponding coefficient is not allowed to be 0. So the reason for this is that, well, we can use these coefficients to write down a bunch of polynomials. Namely, for every face of my subdivision, I can look at the polynomial given by, well, I let the exponents run over the lattice points in my face. And for each lattice point, I use the corresponding complex number as coefficient. And since on the vertices, these coefficients are non-zero, the Newton polytope of my polynomial is the whole face delta. Because, well, it's the convex hull of its vertices, which are included in the support. And so the assumption that we're going to make is that the zero locus of f delta is smooth for all delta. So that's a condition on my choice of coefficients Cm. But it will be satisfied for a general choice of coefficients, and that's all I will care about in practice. So here's our theorem. So I'm going to write down an obstruction which looks quite similar to the obstruction that I showed you before, and well, the relation will be explained in a moment. So what I want to understand is whether a very general hypersurface in the algebraic torus with a given Newton polytope delta is stably rational or not. And so, for instance, this includes hypersurfaces of fixed degree in projective space. That will be the application we're going to see afterwards. And so how can I try to disprove stable rationality? Well, I try to find a subdivision, a regular polyhedral subdivision. And I try to find a choice of coefficients C for this subdivision, such that the following obstruction becomes non-trivial. So I take a sum over all the faces in my subdivision, so faces delta, but which do not lie in the boundary of the polytope. And then for each face, I take the corresponding polynomial f delta. I look at the zero locus of f delta inside the algebraic torus, and I take the stable birational type of this thing. And so finally, I add a sign depending on the codimension of my face. And so this gives me some element in this ring of virtual stable birational types over the complex numbers. And so the theorem says that if the output is not the class of a point, so it's not the class of stably rational varieties, then a very general hypersurface with given Newton polytope delta is not stably rational. So the idea of proof is just to reduce to the case that we've seen before. We want to use all of these combinatorial data to set up a strictly toroidal degeneration. And so by the specialization theorem, to show that a very general hypersurface with Newton polytope delta is not stably rational, it's enough to find one such hypersurface over the field of Bezier series, which is sufficiently general in the sense that it's non-degenerate with respect to the Newton polytope. So non-degeneracy is like the standard genericity condition that is imposed in tropical geometry. I don't want to define it here, but it will be satisfied for a generic choice of coefficients for the polynomial f. And it's something that can be checked easily in practice. And so how to find such a non-degenerate polynomial? Well, we can build from our tropical data a strictly toroidal model, curly X, such that the generic fiber is a toroidal compactification of such a non-degenerate hypersurface with a given Newton polytope. So we want to prove non-stable rationality for this guy. And then in the special fiber, the strata are precisely toroidal compactifications of the hypersurfaces attached to the polynomials f delta, where delta runs through the faces of our subdivision which are not contained in the boundary. And so when I write down the obstruction for this strictly toroidal degeneration, then we get precisely the expression in the previous theorem. So in this sense, our theorem is a special case of the previous one. So let's try and do an example to show how this works. So the example I'm going to show you is sufficiently simple to write down a strictly toroidal degeneration by hand. There are more complicated applications, for instance, to hypersurfaces in products of projective spaces, where working it out by hand is no longer an option, and you really need combinatorial tools provided by tropical geometry. But just for the sake of pedagogy, and because it's a neat application, I'm going to do the example of the quartic fivefold. So the Newton polytope of a general quartic fivefold is just 4 times the standard simplex in R6. Because in general case, I assume that all possible terms occur with a non-zero coefficient. And so in particular, the convex hull of the support will just be 4 times the standard simplex in R6. And so in order to generate my degeneration, I'm going to make a subdivision. And the subdivision that I'm going to create is obtained by inserting the face that is given by slicing with a hyperplane defined by sum of the sum of x1 up to x5 plus 2 times x6 is equal to 4. And so the new phase that I introduce is the Newton polytope of a quartic double fourfold. And this is how eventually our induction is going to work. We are going to deduce non-stable rationality of a general quartic fivefold from the non-stable rationality of a very general quartic double fourfold. So the result of this subdivision is that I've broken up my polytope into 2 isomorphic pieces, delta 1 and delta 2, one above the slice and one below, and they intersect along my slice delta 0. So I've made a cartoon picture in low dimension just to illustrate a bit better what is going on. So what we're doing here is we start from 4 times the standard 3 simplex. So the big orange simplex is the Newton polytope of a general quartic surface. So this would correspond to a K3 surface. And then I'm decomposing it by slicing along the blue triangle. So in the blue triangle, you recognize the Newton polytope of our double quartic curve. So that's Newton polytope of an elliptic curve. And this subdivides the big simplex into 2 pieces, which are the Newton polytopes of quartic double threefolds. Quartic double surfaces, which are del pezzo surfaces. So the corresponding degeneration would degenerate my quartic surface, my K3 surface, into a union of 2 del pezzo surfaces intersecting along an elliptic curve. And this degeneration would be a very highbrow way of proving that a K3 surface is not stably rational. You could deduce it from a non-stable rationality of an elliptic curve. Of course, this type of argument is huge overkill, but it becomes relevant if we increase the dimension. And so to run the calculation, we are going to choose our coefficients Cm in a general way. Except that I want that the symmetry of my picture is preserved. And so we've seen that these two faces of maximal dimension, delta 1 and delta 2, are symmetric. They are mirror symmetric around the blue slice. And so I want to pick coefficients for my lattice points in such a way that this symmetry is preserved. And then I can compute the tropical obstruction. So I take a sum over all the faces delta of my subdivision, which are not contained in the boundary. And for each of these faces, I look at a stable birational type of the corresponding polynomial f delta. And I add a sign which depends on the codimension of the face. So in my picture, I just have 3 faces which are not contained in the boundary, namely my 2 faces of maximal dimension and my blue face of codimension 1. Get 2 positive contributions from delta 1 and delta 2, and then I get 1 negative contribution from delta 0. And now, since I've been careful to preserve the symmetry in the picture, we actually know that the 0 loci of f delta 1 and f delta 2 are isomorphic to each other. Because I can perform a unimodular transformation of my lattice, which corresponds to a change of coordinates on the torus, transforming one hypersurface into the other. And so what I get is twice the stable birational type of f delta 1 minus the stable birational type of f delta 0. And so I want to show that this thing is non-trivial, and the easiest way to do this is to look modulo 2. So if I reduce modulo 2, then the only thing that survives is the stable birational type of the zero locus of f delta 0. And as I said before, zero locus of f delta 0 is quartic double fourfold, which will be general because I've chosen my coefficients in a general way. And fortunately, we know by the work of Hassett, Pirutka, and Schinkel that a very general quartic double fourfold is not stably rational. So this means that the class that we end up with is not the class of a point, even modulo 2. So it was not the class of, so this means that our obstruction is not the class of a point. And the conclusion is that generic fiber of our degeneration, meaning a general hypersurface with Newton polytope delta, is non-stably rational. And so this is how one gets the non-stable rationality of a very general quartic fivefold. So I fear that I've been a bit fast since I'm actually ahead of time, which is unusual. So to compensate, I'll be more than happy to answer any questions you have.
Okay, thank you very much, firstly. Are there any questions?
Hey, I have a question. So this specialization stuff uses weak factorization, but that technology has improved a lot recently, right? So, for example, do we know from could we use this kind of argument to show that, say, unirational parametrization specialize by Abramovich-Temkin or something like this?
Yeah, so it would be great if we could get similar results for unirationality. The problem there is that I don't know how to set up an equivalence relation which contains the unirational varieties as one particular class. And yeah, somehow that's the main obstruction. The whole formalism works because I don't only know what stably rational guys are, but I also have a suitable equivalence relation that I can use to identify other birational types in this way. I know that Dan has tried to come up with a trick where you look at an equivariant version or where you look at Galois covers in a certain way, but as far as I know, things haven't worked out yet. So I think it's an extremely interesting question, but I don't know how to proceed for precisely this reason.
Thanks.
Oh, Johannes, I have a question. It's a bit stupid. So there are lots of stories behind this. I mean, you told us most of it. So it all started from Voisin's degeneration method. And the idea always is to go to some central fiber where you know things fail, and then you get your conclusion. Am I right that the heart of your new thing is that you have that plus this induction, right?
That's right. So yeah, I would say the main difference between this approach and the other specialization techniques is that we have a condition of irreducibility on a special fiber. And in applications, it's actually very important that we're able to deduce non-stable rationality by looking at the geometry of the deeper strata in the special fiber. So like in the final application, the non-trivial contribution came not from a stratum of maximal dimension, but from a stratum of codimension 1. And so I think indeed that the power of this method is precisely that you get this induction mechanism on the dimension as well. At the same time, the weakness is that you can never produce non-stable rationality out of thin air. So you always need a non-trivial input. Which
I was going to say that. So because of this, you can't say anything about cubic.
That's right. So you need enough room to degenerate into things of lower dimension, but which are sufficiently rich in geometry to have a chance of being non-stably rational. That's right.
It's beautiful anyway. Thanks. Yeah.
Thanks.
I have a naive question. Do you think is it possible, and does it make sense to extend this result to slightly more general singularities of the degeneration, not toroidal, but something slightly more general, like, I don't know, DLT?
DLT is probably a bit too much to hope for, but you're absolutely correct that there are. So in the paper with Yevgeny, we try to give some kind of class of singularities that one could work with. For instance, there we look at degenerations into irreducible varieties with ordinary double point singularities, but not necessarily isolated. Because that's also a type of application that had been considered in the literature before. But somehow in all of these cases, yeah, the reason why it works is that your singularities are so simple that you can produce an explicit resolution where you control what kind of strata you add in the resolution process. There is some kind of rationality condition on singularities that makes the method work. That shows that the obstruction that you obtain does not alter if you resolve the singularities to get an actual strictly semi-stable or strictly toroidal model. But I don't know a broad class of singularities which have this property. In concrete cases, you can do better, but I don't know how to characterize an interesting class of singularities beyond the strictly toroidal guys, which have this property.
So overall, your opinion is that generalizing the singularity class probably does not add you more power when using this method.
Yeah, in a sense, well, not in the way that that I can see, because for these singularities, the hidden trick is just that the resolution is so easy that you could have worked with the resolution from the start. Mm-hmm. But I mean, it's perfectly possible that there are some deeper and more subtle results in singularity theory that allow you to enlarge the class of singularities. But I don't have a candidate for a suitable class in that direction.
Okay.
Any further questions? Then let's thank Johannes again. So something of a tradition of Cow is that we usually go to the pub after the talks. So obviously we can't do that at the moment, but a few of us are likely to stick around here and just generally have a chat and maybe a beer for a little bit. So anyone is welcome to stick around if they just want to talk to somebody whom they do not live with, for instance, which is a pleasure we don't get very much in the UK at the moment.